This year, we decided to focus our project on the ever so prevalent Alzheimer's disease.
Alzheimer's is basically a progressive neurological condition that mainly affects memory, thinking, and behavior. The percentage of people with Alzheimer's increases dramatically with age, with over one third of people over the age of 85 suffering from it. It is the most common cause of dementia, with 55 million people in the world suffering from it and 1.5 million dying each year due to it. Moreover, the number of Alzheimer's patients has been increasing each year.
Due to the low level of research and incomplete understanding of the progression of Alzheimer's disease, diagnosing AD has been a huge challenge. Potential theories regarding the progression of Alzheimer's disease include chronic neuronal stress, convergence of factors, hypoxia, inflammation, mitochondrial dysfunction, the presence of multiple pathologies, oxidative stress, and nutrient deprivation. Existing AD diagnosis typically relies on the presence of the plaque deposits formed by amyloid beta and the neurofibril tangles formed by tau protein. MRI scans, CT scans, and PET scans are quite regularly used for the diagnosis of AD, but they come with their own drawbacks. While being super expensive and inaccessible to a lot of the rural population, these scans cannot directly detect amyloid beta plaques. CT scans especially detect brain atrophy, which is not unique to AD, thus making the diagnosis non-specific. Cerebrospinal fluid tests are also performed, which require a lumbar puncture, an invasive sampling method that makes most patients really uncomfortable, and sometimes even involve a lot of medical complications. Amyloid beta and tau protein levels are normally checked in a CSF test. Symptoms of Alzheimer's disease are often confused with normal signs of aging. Furthermore, the lack of awareness about Alzheimer's disease worsens the case. So, early and accessible diagnosis can serve both as an important complement to the goal of raising awareness and also give families and our healthcare infrastructure sufficient time to plan and arrange care for the elderly.
To tackle all of these issues once and for all, we have come up with Neurasense. Neurasense is an aptamer-based, rapid, sensitive, and non-invasive test that aids in early detection of Alzheimer's. Our potential kit utilizes a salivary sample that can check for the presence of two biomarkers, namely lactoferrin and the already well-researched upon amyloid beta. Lactoferrin is found in many biological fluids, and recent research dictates that low levels of lactoferrin in saliva might be an indicator of a developing Alzheimer's disease. Aptamers are essentially single-stranded DNA or RNA that bind specific target molecules with high affinity and specificity. Their target molecules can be proteins, nucleic acids, small molecules, and even viruses, making them extremely versatile. They're also easily chemically modifiable to become more stable, increase shelf life, increase binding, and incorporate other properties of our interest. We utilize known aptamers specific to lactoferrin and amyloid beta for our Alzheimer's diagnostic kit. Building upon this knowledge, we tested the binding ability of the aptamers for these respective proteins using methods we will now explain.
Trial portion basically has three parts: molecular docking, molecular dynamics, and simulation analysis. We have picked amyloid beta and lactoferrin, for which we had downloaded the PDB structures on RCSP. For amyloid beta, we picked both fibril and its monomeric form and checked its binding with our aptamer. For lactoferrin, we picked the part from IGEN part registry. We characterized its structure using MFold and Shao lab and performed docking using HEDOC, where we obtained two clusters of structures and the plots of electrostatic energy and van der Waals energy plot against the interface RMST. Through HEDOC scores, we obtained the best structure clusters. For GROMACS MD simulation, we picked the 50 nanosecond simulation time and 0.15 molar KCl with input files generated from CHARM GY, where the force field picked was CHARM 36M. For the three structures, we obtained the RMST of the aptamer with respect to protein, where the third structure was highly unstable. We used the RMSF plots of structure 1 and 2 for the mean square fluctuations, where structure 1 showed stability. Gyration plots also confirm our observations. To compare structure 1 and 2, we used hydrogen bond plots which were nearly identical for the lactoferrin aptamers. Similarly, amyloid beta 42, we picked the monomeric and fibril structure for analysis. We reviewed the literature and picked DNA aptamer and TSO0508 as aptamers. This was further confirmed by the process of molecular docking using HEDOC 2.4 server, accessing their highly effective protein nucleic acid docking to conduct docking analysis of the following aptamers, while finding the best docking pose and confirmation for further molecular dynamics analysis. For the monomeric form, the possible clusters for docking containing different conformations were plotted for various thermodynamic parameters. Using the plots like energy versus interface RMSD, van der Waals forces versus interface RMSD, and HEDOC score versus interface RMSD, we can easily conclude that cluster 8 contains the best conformation for molecular dynamics analysis. We do the similar such analysis for the fibril structure to find the best structure cluster. For the amyloid beta, we first conducted a self-run of the monomeric structure for 125 nanoseconds to understand the stability of protein. Using backbone to protein RMSD and the radius of gyration plots, we can see the RMSD curve smoothing and stabilizing while the gyration radius reduces. So we could set the simulation time between 50 nanoseconds to 100 nanoseconds. For monomer amyloid beta, it being a small protein, we picked 100 nanosecond simulation time in 0.15 molar KCl plus MgCl2 solution and simulated it for the TS0508 and DNA aptamer best clusters which we analyzed earlier. For the four structures of TS0508, RMSD is showing high spikes, which implies we need to simulate for the long time. But among all structures, structure 4 is the structure with highest stability as we analyze the radius of gyration and RMSF plots. To understand more of the stability, we have to simulate for it a longer time. We compare it with the DNA aptamer. We can see how both aptamers behave. We can see after early equilibration, the DNA aptamer also gives pretty good results in the wet lab experiments, even comparable to the best structure from the other aptamer clusters. Hence, we found the best docked structure for the biomarker above. For the fibril structure, we do similar analysis at 50 nanoseconds for both the TS0508 structures and the DNA aptamer structures. Here we can clearly see that one conformation of DNA aptamer is completely out of picture with high RMSD and higher deviations. We compared the rest of the three structures. We can also check the plots of radius of gyration to see if the conformation is changing quickly or not, or high the value is. In the graph, we can see the radius of gyration for the DNA aptamer's first structure is nearly constant and it's high, which further affirms we can use it as a best aptamer. The RMS value of aptamer also changes, which highlights the potential sites of mutation and hence the important residues in the protein. Hence, we found the best docking pose for the fibril structure. For further work, we can simulate for the higher time, keeping in mind the computational power as well as keep in check the sites of mutations to further improve the aptamer structure.
So moving on to ITC, which is most commonly referred to as isothermal titration calorimetry. As the name suggests, it combined the two techniques of titration and calorimetry at a constant temperature. It is primarily used to study the reaction and interactions between macromolecules in a solution. It can give thermodynamic parameters such as the enthalpy change, entropy change, the stoichiometry of the reaction, and most importantly, the binding affinity, which is referred to as KD. The reaction can be divided into four steps. Initial equilibration. The macromolecules are loaded into the sample cell and the ITC syringe. Titration. One macromolecule is released in the form of small injections. Heat exchange measurement, in which thermodynamic parameters are measured after each injection. Data analysis. Software is used to find valuable insights from the data generated. DNA aptamers and lactoferrin were ordered from IDT and Sigma Aldrich respectively. ITC machine was washed using deionized water and phosphate buffer sequentially. 40 microliter of 176 micromolar DNA aptamer working solution was loaded in the primary cell of ITC. 300 microliter or 20 micromolar lactoferrin working solution was loaded in the specialized ITC syringe and loaded in the sample cell of ITC. Reaction parameters were set as follow. The differential power versus time graph showed an initial exothermic reaction due to heat being released upon DNA aptamer protein binding. The reaction quickly becomes endothermic in nature due to denaturation of protein leading to conformational change. A strong KD value was obtained, which signified strong bonding between aptamer and protein. A total of 8 aptamer molecules were binding to the single lactoferrin molecule, indicating insufficient protein quantity. Despite binding occurring, the reaction becomes endothermic too quickly, indicating that protein starts denaturing with only a small quantity of aptamer being utilized. Thus, to compensate for the low amount of lactoferrin, we used 40 micromolar lactoferrin solution in a second iteration. All the other reaction parameters were set similar to protocol 1. The graph obtained from this iteration was much more balanced and fit all titration data points well. The KD remained the same and binding still occurred. A total of 4 aptamer molecules were binding to a single lactoferrin molecule.
Proceeding from our literature review, MD simulations, and ITC data, we decided to work with the lactoferrin aptamer. The proposed kit we intend to make is an electrochemical aptasensor owing to its miniaturization potential, cost, and sensitivity.
The basic design involves the immobilization of aptamers on electrodes, and our chosen strategy for this exploits the gold electrode's affinity for creating strong sulfur-gold bonds with thiol-modified aptamers. These form a self-assembly monolayer on the electrode along with our chosen spacers. Spacers are blocking agents that prevent the fouling of aptamers and ensure that they stand upright. They also help cover exposed surfaces on the electrode and ensure the detected signal is only from the binding event. In an electrochemical aptasensor, the aptamer is a sensing element. On binding to the biomarker, the conformational change in the aptamer creates a change in the signal generated by the electrode, which is quantified by a potentiostat, a device that controls the electrode potential and converts the corresponding current to digitally analyzed data. This data is then plotted to a calibration curve to model the behavior of the sensor in different concentrations of our biomarker. I'll briefly run through our procedure. To protect thiol grooves, aptamers are shipped in an oxidized form. We reduce the disulfide bonds using TTT and prepared stock solutions of our proteins, aptamers, and blocking agents. Then we tested out several immobilization strategies, varying the spaces used and their ratios, and also tested the sensing thresholds for 11 concentrations of lactoferrin from 0.1 microgram per milliliter to 16 microgram per milliliter. All results were analyzed using cyclic voltammetry or differential pulse voltammetry, and corresponding peak currents were plotted against lactoferrin concentrations. Our first round of electrode studies were conducted with aptamer plus MCH screen printed gold electrodes. Here, we only proceeded with those electrodes that were showing a stable, decreased dPV current range for sensing. This was around 50 microampere compared to the 70 microampere for bare electrodes. Similarly, aptamer plus MCH plus DTT immobilized electrodes were tested with a DTT to aptamer ratio of 10:1, and lactoferrin sensing was tested with the stable electrodes. The electrodes with DTT, most probably due to a lack of available aptamers for binding, quickly reached saturation in a couple of concentrations. These aptasensors also showed barely any change in current, making meaningful sensing difficult. The electrodes that were only backfilled with MCH were more promising. However, on using analyte volumes of 10 microliter, these also reached saturation soon. On trying again with 3 microliter, however, we were able to obtain stable, distinguishable, decreasing dPV currents for increasing concentrations, only reaching saturation around 14 microgram per milliliter. On plotting our obtained current values against the corresponding concentrations, we were able to establish a linear relationship between the concentrations 4 microgram per milliliter and 14 microgram per milliliter, with an R-square value of 0.98, which establishes a reliable linear correlation and falls well within the required range discussed for Alzheimer's patient saliva versus a healthy patient saliva.
Alzheimer's is a rapidly growing burden on the healthcare system, especially in India, where awareness is lacking and support systems are insufficient. This often results in family members having to stay home to care for their elderly relatives, facing financial and emotional strain. These challenges are further complicated by urbanization and disintegration of traditional joint family units. Stigma and lack of awareness about neurodegenerative diseases leads to resistance to getting tested and seek medical attention. In such a landscape, engaging with stakeholders to shape the design of our kit and conducting outreach are equally important parts of solving the problem at hand. Our journey led us to Vanprasth Ashram, a unique elderly community in Uttarakhand. Interactions with residents and caregivers like Shama Devi ji helped us empathize with their struggle in caring for Alzheimer's patients and recognize the urgent need for better trained care professionals in India. Our conversation with Rekha ji, whose husband was diagnosed early, emphasized the significance of early detection as they were able to manage his condition better with medication and care. As we explored wet lab procedures, we collaborated with Dr. Kalyan Kumar Sadhu, an expert in nanobiointerfacial chemistry and biomolecule detection. Dr. Sadhu's research focused on detecting amyloid beta monomer. We talked about the nature of a beta monomer and the need for extensive research into their specific forms found in saliva. Ethical considerations, clinical trials, and the need for scalability were discussed. In collaboration with IISER Thiruvananthapuram, awareness-raising efforts involved survey and interaction with the public to gauge their understanding of Alzheimer's and discuss our project and existing diagnostic tools with them. Conversations with a neurologist, Dr. Rajesh Patel, offered us a comprehensive medical perspective, explaining the stages of Alzheimer's and drawbacks of the existing diagnostic tests, such as MMSE, highlighting cultural bias and limited scope. We saw a critical need for a biomarker-based point-of-care test that removes subjectivity from diagnostic processes. Moving on to our education endeavors. Now, we believe that scientific knowledge should be easily accessible to aspiring students and learners. Awareness about the potential and more recent advancement in technologies should be effectively communicated through the scientific communities, and an extensive kinship must be maintained across the community. Our primary aim is to educate and inspire the diverse audience about the exciting world of synthetic biology through the workshop and the educational initiatives that we took.